to show you some results looking at galaxy evolution in various environments. So I'll talk about some of my results looking at morphology and some other results from the rest of our group as well. So as you all probably know, IllustrisTNG is the newer version of the original Illustris model, which has had several improvements made to it, mainly with regards to the stellar and AGN feedback models. And these improvements have meant that we've gotten some really good results from IllustrisTNG. So for example, this is the Pilipich et al. Paper from 2018 showing that the galaxy stellar mass functions are pretty reasonable out to redshifts of even 4. This is the Nelson et al. Paper from 2018 showing that there's quantitative agreement between the color bimodality in IllustrisTNG and SDSS. And you just saw this result from Vicente Rodriguez-Gomez looking at the optical morphologies that are also doing well. And all these three are important to the stuff that I'm going to show you in a little bit. So what I'm looking at is galaxy morphologies in cluster environments and trying to understand what is the role that the environment plays in transforming morphologies, if at all, to what degree these transformations happen, at what rate do they happen, what environmental factors are important for it, and also how does this compare to things like gas removal and star formation quenching. So this is the data set we're working with, the TNG 100 simulation. I'm looking at galaxies that are within the virial radius of clusters of 10 to the 14 and above. And we're looking at stellar masses of 5 times 10 to the 9 and above. And I use 2 different morphological indicators. The first is the circularity fraction following Gandhali et al., which is basically the mass fraction of stellar particles above a given circularity, which means that they form part of the disk. And secondly, the 3D principal axis ratios calculated in a shell at the half mass radius. And I'm only going to be focusing on galaxies that were disks at the time of accretion. And so the first thing we can ask is, does the environment actually play a role in morphology? So this is the distribution of morphology versus stellar mass, and these are the cluster disks. And then we also look at a control sample, which are mass matched at the time of accretion, and which remain centrals right down to redshift 0. So you can see that we start out with fairly similar distributions of morphology. And then we can follow these galaxies to redshift 0, and you can see, yes, there is an impact of environment. So the cluster disks are almost exclusively non-disks by redshift 0, whereas the control disks remain fairly disky, although at the high mass end, you do get a population that are non-disky at redshift 0. We can do the same thing with the 3D shapes. So I've separated the galaxies into stellar mass spins here, so a low mass to high mass. And so we can start with a slightly different selection of galaxies based on their shapes. And you'll see that spheroidal galaxies will live here, and elongated or prolate galaxies will live here. And so if we go to redshift 0, for the cluster disks, you'll find that at the low mass end, galaxies tend to become spheroidal when they become non-disky, whereas at the higher mass ends, we get this population of elongated galaxies. And there's good evidence to suggest that those are actually galaxies with pretty strong bars. When you look at the control galaxies, first of all, most of them tend to remain disky, as we saw before. But at the high mass end, they tend to become spheroidal, whereas at the intermediate mass, you do find this elongated population as well. So the next thing to look at is the rate of transformation of morphology of these galaxies. So again, in these stellar mass spins, what I'm looking at is the average circularity fraction versus time since accretion. And the dashed lines are the same in all 3 panels, and they show the average for the entire sample. And we're only looking at galaxies that are non-disky at redshift 0, which is like 95% of the cluster sample, but sort of 40 to 60% of the control sample, depending on the stellar mass spin. So what you'll find is that the green lines, which are the cluster sample, all lie right on top of the solid line, which means that they evolve at pretty much the same rate regardless of stellar mass, whereas the control galaxies actually have different rates of evolution depending on their stellar mass. So lower mass galaxies evolve at lower rates than the higher mass galaxies. So what this is telling us is that the environment has the secondary effect where it's speeding up the morphological evolution of lower mass galaxies so that they essentially match up with the evolution rate of the higher mass galaxies as well. So we've looked at various environmental factors that could affect this rate of change. I'm just showing you one of these for the intermediate mass galaxies, because this is probably the one that actually made a big difference. So you can see that these 4 green lines are quartiles of pericentric distance, which is the closest distance the galaxy's ever had to the cluster center. And as you would expect, probably, the galaxies that have had the closest pericentric passages are the ones that evolve fastest. The galaxies that have had the farthest pericentric distances evolve slower on average. We've also looked at some intrinsic factors. This is one that I'm showing you looking at the gas to stellar mass ratio. And what we find is that, at least at the high mass end, it looks like galaxies that had more gas to begin with at accretion tend to become non-disky at slower rates compared to galaxies that had less mass. We probably think this is because there's enough gas to replenish the disk, but I'm not sure yet. It's still something that I'm looking into. And then finally, looking at the evolution of morphology versus various other properties. So this is looking at the average evolution of morphology, or the circularity fraction here. Gas mass, stellar mass, and specific star formation rate. This is just the intermediate mass bin. And we've normalized by the values at accretion so that we can compare all 4 quantities. And what you see here for the cluster disks is that the galaxies lose most of their gas mass fairly quickly and therefore quench very quickly, because that's the way the Illustris model works. So the quenching happens very quickly, whereas the morphological transformation takes a much longer time. And also the stellar mass, you can see, the growth of stellar mass is reduced quite a bit. Whereas in the control sample, the galaxies continue to build their stellar masses, obviously, but also retain their gas mass, and so their morphological transformation is not as different in rate compared to the cluster disks. So I'm going to use this slide to jump to 3 projects that, that different people in our group are working on, looking at the stellar mass-halo mass relation, which is related to the increase in the stellar mass of the cluster galaxies, gas removal through ramp pressure stripping, and also star formation quenching. I'll show you some results from a few different people for that. So this is work that we're still working on by Christoph Engler, who's a PhD student in our group, looking at the differences between the stellar mass-halo mass relation between centrals and satellites. So you can see that the satellites have lower dark matter masses for the same stellar masses, which is likely due to tidal stripping, which removes quite a lot of the dark matter mass but doesn't touch the stellar mass as much. And so he's looking at various reasons to explain the scatter. First of all, you can see that this effect is largest in really high mass halos, and not as big in smaller mass hosts of 10 to the 12, 10 to the 13 clusters. I mean, they're not really clusters at that mass. And also looking at various other properties, mostly orbital properties, that can also affect this scatter. So in bins of cluster mass, he's looking at separating the galaxies by quartiles of cluster-centric distance. I think this is redshift 0, but he's also looked at pericentric distance. And again, it's what you would think of intuitively, which is that galaxies that have had very close passages to the cluster center tend to have this enlarged effect where they have very high stellar masses for what you would expect for their dark matter masses. And the same thing is true when you look at quartiles of infall time. So galaxies that were accreted very early on tend to have much higher stellar mass to halo mass relations compared to galaxies that were accreted fairly early. So right now this work includes TNG 100 and 300, but TNG 50 is just become available in the last couple of months. So Chris is working on including the TNG 50 results, and they'll be out soon, hopefully within a month or so. Okay, Moving on to gas removal, this is work by Kyun Yoon, who's another PhD student in our group. And his project is all about looking at jellyfish galaxies, or galaxies that show significant gas stripping. So this is just a nice gallery of all the jellyfish galaxies that we visually classified at 4 different redshifts. So there's a pretty big population of them. There were about 800 across the 4 redshifts. And you can see quite a lot of them actually have these really nice bow shocks associated with them as well. So this paper is already out looking at the initial population at these 4 redshifts. I'll just show you a couple of things. So looking at the infall time distribution of these galaxies, so this is all of the galaxies at redshift 0. These are galaxies that still have gas. And then the blue and red are jellyfish galaxies. And what this shows you is that these galaxies were fairly recent infallers. They fell in within the last sort of couple of gigayears. And secondly, looking at their distribution in this Ram pressure versus Mach number plane, you can see that these galaxies, the colored points are the ones, they tend to have higher Ram pressure and also have higher Mach numbers compared to their surrounding ICM. So this work is already out. He's working on generating a citizen science project so that we can visually classify more of these galaxies, so that we can actually follow the evolution of these jellyfish galaxies. So hopefully that work will come out soon as well. And then lastly, this is work by Martina Donari, who's another postdoc in our group, looking at all kinds of properties of quench fractions and quenching timescales in TNGs, 100 and 300. This is the quench fraction of the centrals, and you can see the big improvement between the original Illustris and now IllustrisTNG, where the quench fractions are fairly high at the higher mass end and fairly low at the low mass end, and in good agreement with observational data. Similarly with satellites, where you have very high satellite fractions, much higher than the centrals at pretty much all stellar masses except the most massive galaxies. Also looking at these galaxies separated by host masses, what we find is, what Martina finds is that the highest mass hosts tend to have the highest quench fractions. I mean, at 10 to the 14 and above in TNG 300, 14.5 and above, sorry, the quench fractions are almost 95% at all stellar masses. And similarly, she calculates quenching timescales for these galaxies, and so you can see that at the most massive clusters, the quenching timescales are sort of 1 to 2 gigayears. At the lower mass end, sort of 3 to 4 gigayears. And I didn't put the plot in here, but lower mass satellites tend to quench faster than centrals, which I didn't show you. So hopefully this work will be out soon as well. Okay, I'll leave up a summary of the morphology results, and I'll stop there. Thank you.
Questions, starting with students.
I don't know that he looked at this specifically. My guess would be that the fact that you actually have to be able to see the tidal stripping, the Ram pressure stripping phenomena. So galaxies that fell in earlier might have had jellyfish stages and have since lost all of their gas. So I think the galaxies that we're seeing right now are the ones that have fallen in within the last couple of gigayears. But this is just my guess. This is not something Kyun's looked at yet. Mm-hmm.
And you mentioned that they are differentially large galaxies, and I was just wondering if you look at those specific populations, sort of trace back their history and see if they had any differential urging or anything like that that's causing them to be elongated. I'm just curious, have you looked at their urging history or anything?
I've looked at their individual histories of like stellar mass growth and so on. I don't think I found anything that there was a really high merger fraction. But that's a good point. I will look into that. when I say that there's probably a strong bar, it's because we find that for pretty much most of their lifetimes, for all of these galaxies, regardless of where they end up, the minor axis is pretty well aligned with the angular momentum axis, so it's like a rod kind of rotating in the plane. But these they can go out to fairly large distances. So yeah, that merger history is another. I should look into that. Yeah.
So I'll take a few more questions while the next speaker, if you could come up and get ready. So, yeah, over there.
On the topic of brain pressure stripping, so these jellyfish galaxies are striking, beautiful, and all this, but aren't they actually being the tip of the iceberg in terms of what's happening in clusters? I mean, there's certain times that you have these remarkable stripped tails, and possibly the star formation happening inside those. But what about quenching that's happening on longer time scales through starvation and the stripping of actually certain block medium, which is going to be far too reduced to detect those types of features?
Sure. So I think Kuhn's work is not saying that this is the only mode of quenching in clusters. We're specifically looking at just jellyfish galaxies and specifically looking at ram pressure stripping. But that's not to say that there aren't galaxies that have gone through other quenching mechanisms.
The question is the relative amount of quenching happening in those types of dramatic events versus the longer time scale type starvation episodes.
Mm-hmm.
Do you have a sense of what the relative is?
Not really. He looked at just this sample, but it's difficult to quantify if they had other. Sorry, I should mention that we have only snapshots right now, so we don't have full histories for these galaxies, so we can't tell when the jellyfish phase began or anything like that. But hopefully, in the next project, we probably will be able to do that.
Okay, so we're gonna stop the question and answer session here. Let's thank the Gandhali again. Thank you.